Okay, hello everyone. We are very sorry for the delay. And I'm Kai Gu from Nanjing University, and I'm very honored to host this session. And this afternoon we have 6 speakers. And the first speaker is Professor Xuanmei Fan. Professor Fan is a professor in the College of Environment and Civil Engineering at the Chengdu University of Technology. She is a recipient of Richard Ward's Award of IAEG in 2016. Her research interests cover earthquake-induced geological hazards, application of remote sensing and geographic information systems in geological engineering, risk assessment and prevention research of geological hazards, etc. Today, her topic is what have we learned from earthquake-induced chains of geological hazards? Let's welcome Professor Fan.
Thank you very much, Professor Gu, for your introduction. So let me share my screen. Can you see my presentation?
Yes, we can.
Okay, is it on the full screen or on the?
Yes, it's full screen.
Okay. So first, I would like to thank Professor Shibing and Professor Chao Shentang for inviting me to give this presentation on the ISEG. So I'm quite new to your committee. I'm working probably also on something a bit different from the presentations from yesterday and today. So as Professor Gu already introduced, so I will skip the self-introduction part. I'm going to talk about the earthquake-induced chains of geological hazards today. So just to give you a kind of short introduction of what I'm talking about, because I think some of you may not really know when earthquake happen, why it will trigger so many landslides. So I'll first show you a piece of animation. So as you can see, this earthquake, due to the strong bounce, can trigger a lot of landslides. And this, is it okay? It's stopped, sorry. Just a moment. Yeah, so some of the landslides in the vicinity of rivers can trigger landslide dams. And these dams, they are quite weak. So especially the was dam breaking and dam causing problems. So this is just a piece of animation to give you a direct feeling of it's a type of earthquake-induced chains of geological hazards. So some landslides in the vicinity of rivers can block river and forming landslide dams, and the dams can fill during the, especially when you have heavy rain, and then causing further flooding. And this is this slide shows you the situation of the 2008 Wenchuan earthquake. So this earthquake, you know, occurred in 2008 in the southwest part of China, and with magnitude 7.9. It killed about 87,000 people, and 1/3 of the total death toll was actually caused by landslides and secondary geological hazards. So, and this earthquake triggered more than 60,000 landslides and also induced numerous post-seismic landslides and debris flows. So that's why it has attracted attention from all over the world. This is some literature statistics we did in 2018 at the 10th year's anniversary of the Wenchuan earthquake. So as you can see, there were about more than 6,000 papers published on the Wenchuan earthquake, and about 1,000 papers are directly on the geological hazards induced by the earthquake. So this slide gives you a summarization of the chains of geological hazards in the mountainous regions. So as you can see from here, in the right circle represents for the coseismic stage is actually what I have already showed you during the animation. So during the earthquake, it can trigger kind of different types of landslides. And these landslides, some of them can causing further like dam breaking, flooding problem. Sorry, I don't know why, but the slide is jumping itself. And some of these landslides after the earthquake can be remobilized or reactivated, and some can even convert it into debris flow and further transport sediments into river. As you can see from here, the riverbed can be rising during the large amount of loose sediments transport from hill slope to the river. And as you can imagine, after riverbed rising, it will also causing the increase of flooding for the future. So since 2008, I have been working on the chains of geological hazards, and I summarized it here. So first, we were working on coseismic landslides. What I'm saying co-seismic, it means when the earthquake happened, it simultaneously triggers some geological hazards. So we did inventory and analyze the spatial distribution pattern and their controls. And after that, we were moving like with a timeline to the post-seismic landslides and post-seismic debris flows. So I will give you a kind of short overview of all these stages in the coming slides. So first of all, we are trying to understand, like during the earthquake, why it can cause so many landslides and what is the spatial distribution pattern of these landslides. So we found there are 3 types of controlling factors. The first one is seismic factor. It means distance to fault, fault type, and hanging wall effect, footwall effect. These factors are important, and also like terrain factors, slope, internal relief, etc. And geological factors we all know are lithology, soil type, and geological structure. And the hydrological factors are extremely important for landslide dams, actually. And we also further created an inventory for global earthquake-induced landslides. So this inventory includes 49 earthquake-induced like landslides events. And this is publicly shared with the USGS data repository. And based on this global earthquake inventory, we further analyzed and we found some like kind of general rules for earthquake-induced landslides spatial distribution. As you can see from here, most of landslides actually are concentrated on the hanging wall of the thrusting fault. And it also has very strong distance effect. So within the 5 kilometers close to the fault, the landslide density is highest. And with the increasing of the distance to fault, the landslide density becoming decreasing. And we further developed a model to predict when an earthquake happens, where most probably the landslides will be. So this model actually used artificial intelligence methods based on this global earthquake-induced landslide inventory. To give you a quick summary of this model is, for example, everywhere when an earthquake happens, we can quickly predict where most probably the landslide is going to happen. So this figure actually shows after the Geotechnology earthquake, we did a quick prediction of co-seismic landslides, and the model did a quite good job for prediction the location of co-seismic landslides. And moving from the co-seismic stage to the post-seismic stage, so after the earthquake, our government is facing serious problem with post-seismic landslides and also debris flows. So the key research questions we are trying to address here is how to quantify the evolution of post-seismic geological hazards, and trying to understand what is the pattern and trend of the evolution of post-seismic geological hazards, and trying to find the possible controlling factors, and also create prediction models for future landslide hazards in the region. So first, to understand, like trying to understand how landslide activity change after since after 2008 till now. So we created a multi-temporal inventory for co-seismic, post-seismic landslides. Tracking is an inventory covers the time period for about 12 years after the earthquake. So you can see from here, this figure shows the co-seismic landslides. So all the yellow polygons represents for the co-seismic landslides. And this is the inventory mapped after the first strong rainfall after the earthquake. Different colors, different reddish colors represents for the reactivation of co-seismic landslide deposits, and the red color means the dormant landslides. So as you can see here, in 2011, after a big rainfall event in 2010, most of coseismic landslide deposits become reactivated or remobilized. And this is an inventory after 2013. You can see the reddish regions are becoming less compared to the 2011. That means we have less reactivated landslides and more regions become white color. That means more regions become stable. And now we did this again for 2017, 2015, 17, and 20. I did not show other inventories. And we also mapped the pre-earthquake landslides. These are 2005 and 2007 for comparison reason. So if I plot all this inventory as a volume density, you can see before the earthquakes, this region has quite low landslide density, and this is a coseismic, means earthquake-induced landslide density. And after that, the density become decreasing. And until 2020, this landslide density, the values seems already returned to the pre-earthquake level. And if we further plot this in this graph, you can even see it more clearly. So we can see that after the earthquake, we have the landslide volume become suddenly increased, and then with time it's decreasing. And so far it has been already returned to the pre-earthquake level. And even considering the variation of rainfall, if we do a normalization with rainfall, you can still see the clearly decreasing trend. And then we also checked the evolution of post-seismic landslides in size. So how the magnitude changed over time. As you can see from here, most of the reactivated landslides are actually represents in this yellow color. So these are the remobilization of coseismic landslides. And the new post-seismic landslides are the green ones. They are rather small. So the major type of post-seismic landslides are actually reactivation from the coseismic landslide deposits. And from this graph, you can also see the decreasing trend for the size frequency curve from 2008 to 2020. And 2020 is the green points. They are already very close mixed with the pre-earthquake points, 2005 and 2007. And we are also trying to track how they change on the slope. That means how the material are moving gradually from the slope to the channel. So we found this, sorry, let's jump again. So we found these are the coseismic landslides, and they are mostly concentrated either at the upper part of the slope due to seismic amplification effect or to the channel. And 2011 and 2013, they are pretty followed the coseismic stage distribution pattern. But afterwards, in 2015, 17, and 18, they again becoming more or less similar to the pre-earthquake situation. So we are trying to understand why the landslide activity decay very quickly after the earthquake, let's say within 10 years, is already returned to the pre-earthquake level. And we found one of the controlling factor is what we call it grain size causing. So we found some field evidence. As you can see from here, this is a cross section we found in the field, reviewed the different debris flow deposits from different years. So the bottom one is the oldest debris flow event, and covered on the top is the next event, and on the top is the newest event. You can obviously see that the grain size become causing for the debris flow events. And from the field photo at the same location, you can also see the fine grains. They are easy to be washed away during the first few rainfall events, and then left the coarse grains. And the grain causing can causing permeability changing of the slope, and also the friction cohesion also changing with time. And we also took samples to do grain size distribution analysis from the field. You can also see with time the grain size becoming causing. It means the deposits has much less fine grains compared to 2008. If you compare the 2019 with the 2008 grain size distribution curve. And then the other important factor is revegetation. It can contribute a lot to stabilize the shallow slope failures. Sorry. And this is maybe we first look at the photo. This is a photo I took in the field shortly after the earthquake for one of the big landslide called the Donghekou landslide. And this is a photo again in the more or less from the same angle. And you can see it was taken in 2020, and the landslide is fully covered by vegetation, and it's hardly to be noticed that there was a landslide about 12 years ago. And then we did a Landsat imagery analysis. You can also see this region become revegetated over time. And if we did NDVI analysis with time for pre-earthquake data and post-earthquake data, you can also see the earthquake-induced landslides destroyed a lot of vegetation, causing the NDVI sharply decrease during 2008. But after the earthquake, NDVI values increasing gradually, and now about 85% of the region has been recovered by vegetation after the earthquake. And then we also did a dynamic analysis for the controlling factors. So as you can see from this dynamic factor importance changing over time. And based on this dynamic changing controlling factors, we created a model to predict the post-seismic landslides. And this paper is published on Geophysics Research Letter this year. So if you are interested, you can check the details in this paper. And now let me move to the post-seismic debris flows. So this gives you an idea of post-seismic debris flows. These two images were taken in 2010 and 2011. You can see during the first few rainfall events after the earthquake, almost all catchments has debris flows, and this is the Minjiang River. Almost all catchments has debris flow deposits in the Minjiang River. So in the first few years, the debris flow activity was quite high. And some of this debris flows also causing big problem to the reconstruction side, like this debris flow running to the river, partially blocks the river and causing flooding of the upstream reconstructed inshore side. And this is another catchment. After the earthquake, our government constructed like check dams trying to stop this kind of debris flows, but some of this mitigation works was destroyed because of the activity was so strong. And some check dams was filled up by debris. So from this, you may have a feeling that we probably have underestimated the activity and the magnitude of these debris flows in the first few years after the earthquake when we started designing these mitigation works. And try to understand what is really control the post-seismic debris flows. We created a database for the post-seismic debris flow. including about 500 debris flow events after the earthquake, and also the rainfall data. We have a widely distributed rain gauge network, as you can see the blue dots here. So that help us to understand the triggering rainfall threshold for this debris flow events. So the debris flow activity actually shows different trend from the post-seismic landslides. As I just mentioned, for post-seismic landslides, we have this clearly decade after the earthquake. But for debris flow events, we see they have this fluctuations with the changing intensity of rainfall after the earthquake. And one of the reasons is if we do a sediment budget analysis, we found that actually more than 85% of the co-seismic landslide deposits are still in the mountain regions. So that means in the past 12 years, by the already occurred debris flow sediment transport, it only transported about 10% of the deposits outside of the catchment into the Minjiang River, and 5% are actually stored in the channel, and about 80% are on the hill slope. So that's why we still have kind of debris flow activities continue longer than post-seismic landslides. And in order to better predict post-seismic debris flow activities, we created a numerical simulation model, as you can see from here. It can simulate like which part of the co-seismic landslide deposits can become unstable during the heavy rainfall and how they converted into debris flows. So we did this simulation and compared with real scenarios and found this model actually have quite good prediction power. And this paper has also been published in 2019. And for this model, we also shared our codes. It was developed based on the PC Raster open access platform. So if you are interested in the debris flow simulation, especially after the earthquake situation, you are welcome to also to check the paper and download the codes to run it in your own area. And then we further tested our hypothesis before, because I mentioned the grain size causing and revegetation are the two most important factors we think can control the post-seismic landslide activity and debris flow activity. So we tested it with our model, and it shows also the same results. As you can see here, with grain size causing the rainfall threshold increasing over time, and also revegetation also placing somehow relatively important role for the debris flow activity. But for the early warning of debris flow, we need to understand better, like how their occurrence can be linked with the triggering rainfall intensity and duration. So after the earthquake, we had this schematic graph to put our Wenchuan earthquake data with the 1999 Qiqi earthquake data. So as you can see here, this is the rainfall, hourly rainfall threshold before the earthquake, and after the earthquake, it sharply decreased to only 1/3 of the pre-earthquake level. But with time, it also increasing. And the reason for increasing, I already explained, is because of the changing property of this co-seismic landslide deposits, like grain size causing and revegetation, etc. But no one has been quantified the how the rainfall threshold changing. So what we did is we put all these debris flow events, about more than 1,000 events in more than 200 catchments after the earthquake, and trying to see whether the rainfall threshold has a pattern of changing. So this is the pre-earthquake rainfall threshold is quite high. And if we use this threshold to predict post-earthquake debris flow events, you can see only one event can be predicted. The reason is after the earthquake in 2008, the debris flow rainfall threshold reduced to here, and then with time is increasing. So, but so far it has not yet been returning to the completely to the pre-earthquake level. So that's why on one side we still have quite a lot of deposits in the mountain regions, and then on the other side we have the rainfall threshold still not yet returned to the pre-earthquake level. So that's why we will continue have debris flows in the earthquake region probably for another 10 years or even longer. So that's all I want to present today, and just to give you a quick summary for the recommendations for future directions. I also summarized all this study on the paper we published on Reviews of Geophysics in 2019. If you are interested in this part, you can also check that paper. So we think the challenge for the future is to understand like the interaction between different types of hazards. Like the chain of geological hazards, it always involves different types of hazards. So the interaction, trying to understand their interaction and quantify the interaction is very important. And the quantification of post-seismic landslide inventory in time, space, and in magnitude, we already did a field work on this. But the future challenging is to better analyze the controlling factors, and then to also to do it for more earthquakes, because we built our model now mainly based on the Wenchuan earthquake, and then we hope in the future can look into more earthquakes globally. And then for the prediction of post-seismic debris flows, we created a numerical simulation model, but again, it needs to be tested in more regions. Fortunately, we already tested it, for example, in the geological earthquake and in the Kaikoura earthquake after New Zealand Kaikoura earthquake, sorry. And then the other thing is about trying to create a better model to understand hazard and risk evolving after the earthquake, and trying to apply it in different regions. And then for the long-term impact, we need to create a model together with the geomorphic evolution, trying to understand how the sediment transport and how it affects the long-term landscape evolution. So lastly, I'd like to welcome you to our institute called State Key Laboratory of Geohazard Prevention and Geoenvironment Protection. It's China's only national level laboratory in the field of geohazard and engineering geology. And we are currently recruit new staff members. So if you are interested, you can directly contact me. And we also have a team focusing on the chains of geological hazards in the Tibetan Plateau regions, leading by myself. And then another small advertisement is about our annual course. We have an international research association for large-scale landslides, and this research association offers free course for PhD students and young postdocs for the large-scale landslides, field data collection, monitoring, modeling. So we already organized this course since 2016, and last year we organized the online course. And this year we already opened the call. It will be online course again, but we will have some lectures and a training session for modeling software, and we also have a virtual field trip to lead you to some of the sites which I also presented in today's presentation. So if you check our website, you will find this information. And thank you very much for your attention.
Okay, thank you very much, Professor Fan. Well, the time is perfect, and we all know that earthquake is not a single geohazard, but it can change a lot of, it can induce a lot of other geohazards. So, Professor Fan provided us a very comprehensive understanding of the earthquake-induced change of geological hazards. So we have time for one question. Do we have any questions for Professor Fan? So you can raise your hands and so do we have any questions? Okay, no. Thanks again, Professor Fan. And if you have any questions, you can email to Professor Fan and have conversation privately.
Okay, thank you.
Okay, thank you. Next, we have to slightly adjust our schedule because Professor Pu is slightly delayed. So let's welcome Professor Yaolin Yi from University of from Nanyang Technological University, Singapore. Professor Yi's research interests include ground improvement, sustainable construction materials, and the treatment of contaminated soils and wastes. He is an associate editor of ASC Journal of Materials in Civil Engineering and editorial board member of ISEG Ground Improvement Journal. Today, his topic is compression behavior of tide-derived aggregates, TDA. Well, let's welcome Professor Yi. Professor Yi, you can turn out, you are now muted. Please turn on your voice. Professor Yi, please turn on your voice.
Give me seconds. Okay.
Oh, yes, it's okay now.
Can you see my slides?
Yes, we can see.
Okay, that's good. Okay, thank you, good guy. Long time no see. It's really annoying. My name is Yaolin Yi, and I'm from the Nanyang Technological University, Singapore. And today my topic is about compression behavior of tide-derived aggregate, TDA. Here are the outlines. Give me seconds. Okay, including 4 parts: first, background; second, experiments; and the compression estimation and the conclusions. First, background. The problem is that, as we know, the amount of discarded tides is increasing every year, almost everywhere. And the disposal is a problem, like shown in this picture. Here I list some numbers. I just want to highlight one in Canada because actually I did this research when I was working in Canada in the University of Alberta. Like just in Canada, we have like around 30 million of discarded tides per year. And in Alberta, there's around 5 million. So the problem of the discarded tides include first, land consumption, because it will occupy a lot of land, and especially it has a high risk of catching fire. Here is an example. This happened in 2016 in Spain. Actually, the fire was induced by the discarded tide, and more than 9,000 people excavated. So actually, this is a really big problem. And also, it looks really bad. In Alberta, the background is that actually we try to use this material. We mainly use discarded tide to produce tire-derived aggregate. And it's mainly used for landfill drainage application. But this is a very small market. It cannot consume a lot of discarded tides. So at that time, the problem is try to find out this and in some other ways, it can consume large volume of discarded tiles. And especially in Alberta, we have some special type of discarded tiles, because in other words, usually the tiles are for like for cars or trucks, but in Alberta, if you know Alberta, you know that actually it's very famous for oil sand. So there's some special type of tiles from the heavy machinery. So it's kind of different. So we also focus on this different type of tiles we call off-the-road tiles, because it's not used for on the road. It's just off the road. It's for the oil sand industry. So we call it OTR or OTRT. How to produce TDA? Actually very simple. Just cut this discarded tile into small pieces. But you know, if you want fire size, like for example, if you want to make it fire smaller size, it's cost more. So what we can sense is that there are large volumes between these tiles, because it's kind of just made from the rubbers, and the rubber is easy to deform. So the advantage of this application is that this is not new, but there's still some advantage. The first one, it can consume large quantities of discarded tiles, and it also can reduce use of conventional mineral aggregates, and the very low risk of catch fire, because when used in this application, we bury the tile underground, so there's less risk of catching fire. And also for civil engineering, the TDA is kind of lightweight, because the unit weight or specific gravity is just like 1/3, even half, or around to 1/3 or half of the conventional aggregate. It can be cost effective because it's made from the waste materials. But of course, it depends on the location. If the transportation is too far away, actually it's not that cost effective. What the problem we focus on is about compression. And you just see the picture I showed before. This material is kind of very loose. So it will induce very high compression on the loading in civil engineering. So this performance of this behavior actually govern its design and performance. So how to do this? Similar to soil, which is usually we use like one-dimensional compression test to investigate or study the compression behavior, and then we can use it to calculate or estimate the compression in the field. But the problem is that the particle size for this material is much larger compared to soil. For soil, in geotechnical engineering, we use very small odometer test. Like showing here, the diameter just like 50 millimeter and the height just 20 to 30 millimeter. So it's very small. I think everyone is familiar with this. But for TDA, it should be very large, because the particle size can be higher to 300 millimeter. So we need a very big compression model to do this. And the previous results indicated that actually the size affects a lot. So the problem is that if you want to do the compression test, you need a very big compression model. And also the loading method is also different. So our objective of this research focus on the particle size, loading method, initial void ratio, on the compression behavior of TDA. The question we want to answer is very simple. Is it possible to use small-scale laboratory test on small-sized TDA to estimate the compression of large-sized TDA? Because it's quite practical. We cannot always do very large laboratory test in order to calculate the field test result. But this question actually is quite tricky, because for soil or rock, it's almost impossible, because it's very clear we cannot, based on the one-dimensional compression test of sand, to predict the deformation of rock, right? It's impossible. So But for TDA, if it's possible, that's what we want to answer, because this material actually is simpler. It's just like rubber-tied pieces. So if it's possible, so that's we want to answer this question. So now I'm going to introduce experiments. We did 3 types of compression test. One is small scale laboratory test, relatively small scale. We use small sized TDA. And second, we also did the large scale laboratory test. We used the same TDA as we used in field. And the third one is full scale field test. So we just use very large size TDA. So we want to compare the result from the 3 types of test and to see if there's something in common, if it's possible to use a relatively small scale test to predict the compression for the large scale. So that's the objective of this research. As I mentioned, we focus on many particle size, initial void ratio or unit weight, and then test method. Additionally, in our beta, we also investigate the special type of tire source, we call it OTR. These are 2 pictures showing the material. The first one we call PLTT, so it's passenger and light truck tire. So the normal tires we used on the road. And the second one we call it OTR or OTRT. It's off the road tires. It's used for like heavy machinery, like used for oil sand industry. So the difference is that the second one is much thinner. The first one is very thin. It's very thin. It's like it's plate-like, and the second one is just like rock, right? Looks like the ship. So can we use the same method to predict both materials? So this is another question. And these are the particle size distribution of the materials. So generally, we try different size of materials. And one we call type A. Type A just like has very small size. And second one we type B. So in the small scale laboratory test, we use small sized. And in the field test or large scale laboratory test, we use large size. But additionally, we also test on a very small size. We call type A, this blue line. Small scale laboratory test, and showing here, it's not small, right? Compared with the automated test, it's not small because the diameter is around 0.6 meter and the height is 1.12. Actually, quite big. But compared to the next one I'm going to introduce, this is relatively small. So for this small scale test, we use particle size. The maximum one just 125. So the diameter is more than 4 times of the largest particle size. And the loading, we use different load increments. We apply it immediately and then maintain it until the deformation was steady. We don't have water in it, so it's different from the consolidation test for soil. As I mentioned, we focus on different initial void ratio or unit weights. For the large scale issue here, it's quite large. The diameter is 1.23 meter, and the height is 1.5 meter, and the maximum size is 300 millimeter. So we use exactly the same materials as in the field. And the loading method is different. We do not use the load increments. We use constant deformation rate of 13 millimeter per minute. So remember, the loading methods are different. And because it's quite large, so we only tested on 2 types of sample. One is loose sample, second one is compacted samples. This picture, you can see that it's quite large. This is a PhD working for this test. Actually, so far as I know, it was the largest one in the world, because for one sample we used almost 1 ton of TDA. So it's not convenient to do this large scale compression test. And the third one is field test. Actually, we did a very big excavation pit. The depth is 8 meters, and the the width is 17 on the bottom, and on the top it's 40 meter. So actually, this is a pilot project. It was for a highway embankment construction. So we use this lightweight fill materials. One thing I want to mention that the soil, the native soil actually is very good. It's quite stiff. So the deformation actually is very small, especially we replace with lightweight material. So the deformation below, in the native ground actually is very small. So for the construction, first we do excavation, and then spread the TDAs, and then compaction, and then just do construction layer by layer. And during this process, I forget something. And we have 2 layers of TDA, and in between we have 1 layer of compacted soil to separate it. And for the lower layer, the bottom layer, we measure the pressures, vertical pressures, as well as the deformation. So we can compare the stress and strain behavior of the 3 types of different tests: small scale laboratory test, large scale laboratory test, as well as field test. So that's the instrumentation. Now I'm going to introduce about the experimental result. Here is the vertical stress and the vertical strain curves for POTT. We compare 3 types of result: lab test S, small test, lab test L, large test, and field test. What is quite interesting is that in the field, the deformation or the compression is kind of linear, except for the starting point. This point we didn't measure it because the pressure is very small. But it's quite clear. It's almost linear relationship. But for the laboratory test, it's non-linear. And if we compare it, we can see that in the field we have the smallest water ratio. It has the highest unit weight. So that's the reason it has a very small deformation. So this findings actually agree with other studies, because it's very clear in the field we always measure relatively small deformation, but in laboratory we always measure very large deformation. So the key point is the initial state, is initial unit weight or initial water ratio. For example, on this one, the initial water ratio is 1.92, so it has the largest deformation, even at very small vertical stress, around 20 kPa. And another thing is that although we used 3 different types of tests, but we found that as long as the initial water ratio are close. For example, these 2 circles, this one is for large laboratory test. The initial water ratio is 1.38, and the red circular, the initial water ratio is 1.29. So they are kind of close, but there are 2 different types of tests. One is small scale, second is large scale, and 2 different materials. One is type B, one is type A. So the particle size are quite different, but we can see that actually the compression or the stress strain curves are quite close. So we also found the same result for the OTR, another type of the test for heavy machinery. Again, the field test, the strain and stress curve is kind of linear. And for 2 type of laboratory test, if the initial water ratio are close, for example, the 2 squares, one is for large scale laboratory test, the initial water ratio is 1.46, and the black square 1.51, also quite close, but they are different type of test. Again, the compression results are very close. And these 2 triangles is similar. Initial water ratio 0.98, and the blue one is 0.92. Again, two different types of tests, but the compression curves are quite close. So actually, it seems that the initial water ratio actually control the compression behavior, and the particle size and the loading method actually doesn't affect too much. And this is quite different from what we learned from soil mechanicals, because for soils, the particle size actually matter a lot. And in soil mechanics, we usually plot the water ratio against the vertical stress. So what more interesting is that all the compression curves try to emerge and last. It's indicated they actually have the same law. They follow the same law on the compression. This is for PLTT. No matter the materials, no matter the loading method, no matter the scale. And for OTR, we found the same thing. All the compression curves try to match, try to be together and last. So this was very interesting. And also in soil mechanicals, we usually want to plot it with a semi-scale. So again, I try to match here. This is different from what we know for sand or for clay. For example, for sand, the imaging of compression curve is very difficult unless we have very high stress. For example, here, it seems that they're trying to match, but this is because the soil particles actually has been fractured. So it has been, the soil particles are broken, so they try to get together. This because we have very high content of plastic stream, but for the TDA, most of the deformation is elastic, and they emerge much better compared to here. And for clay, again, it looks like they try to match, but not exactly unless we use normalized water ratio. So the finding means that actually the compression behavior of TDA is simpler compared to soil, compared to sand, compared to clay. So it may be possible we can come up with a simple method to estimate the deformation, vertical deformation, compression. So maybe it's possible to use small-scale laboratory tests to predict the compression for large-scale as well as field-scale compression. So in order to do this, we calculate the compression modulus, because this parameter is commonly used for compression calculation. We calculate the compression modulus for very small load increment using this equation, quite simple equation. And I said, it seems that the water ratio is the dominant factor. So we plot it. We plot the compression modulus against the water ratio. What interesting is that all the points actually try to follow the same line, the same curve. So it means different scale of test with different materials, with different particle size, actually they follow the same compression law. So, and for example, if we know this function based on some laboratory test, we can simply estimate the compression. So the third part is about the validation of this assumption. The method is very simple. Assume that based on small-scale laboratory tests, we can do regression, get this curve, get this function in terms of compression modulus and the water ratio. And then if we assume the loading is very slow, so we can divide the loading process into very small increment. For each increment, we can calculate the compression modulus based on the water ratio, because we know the initial water ratio. So we can start from the first load increment and to the last one. And then we can modify or correct the modulus according to the corrected water ratio. So then we can start from the first part, from the 0 kPa loading to whatever you want. So to verify this assumption, we use just three samples of small-scale laboratory test on PLTT in laboratory test, which I showed before, just based on the 3 lines, the 3 curves, and we do regression. And the R-square not too high, but not too bad, 0.994. So based on this function, we try to predict the result for other tests I just showed you before. And this is prediction for the, again, the small scale test, but on OTR. And we can see that the result actually match really good. The difference between this OTR and this PLTT is that thickness, the particle size distribution actually is similar, and the thickness is quite different because the tire source is different. So, but what we can see that the prediction is good. So at least the particle size or the thickness doesn't affect our prediction. And then we try to predict the large scale laboratory test. Again, all the results are quite good. The difference between the large scale laboratory test and a small scale laboratory test are that they are different TDA thickness, length, and width. So material particle size are quite different. And second, the model size are different. And the sample preparation method are also different. Loading methods are also different. I mentioned one is we use load increment. And the second one we use constant loading rate. So this means actually we can use result from the small scale laboratory test to predict the result for large scale laboratory test. So we also try to do prediction for result published by other authors, for other researchers. Again, as long as we know the initial water ratio accurately, the results are not too bad. And we also try to verify the result with field test, not that good compared to result I showed previously, not that good. And the reason is that in the field, actually, we did not know the initial water ratio accurately. We just have some estimated numbers because we do not know the whole volume of the excavation accurately. We also did not know the whole mass. We measure some of them, but there's a very high variation. So this is a major reason the prediction is not as good as before. But overall, for civil engineering application, I think it's okay because the difference is between 20% to 10%. So actually, it answered our question. That is, it is possible for this special type of material, it is possible to use small-scale laboratory compression test to predict the result for large scale, for field scale. So we answered this question. Now I'm going to summarize some conclusions. The first one, the compressibility of TDA is primarily dominated by the initial water ratio, and the particle size loading method actually has much less influence compared to the water ratio. This is because this material is quite different from the from soil, because it's a very perfect inelastic materials. I mean the particle, because it's just rubber. So it's easy to deform under deformation. So actually, for example, the clogging interlock for the particles actually is quite small. And second, all different type of TDA samples we studied actually have almost the same compression modulus and water ratio relationship, regardless of initial water ratio, particle size, and loading method. So this is very useful for practice. So we can use this to estimate the compression of large size TDA based on the result of small size TDA in laboratory. So it's possible to apply this method for design. And the next I want to emphasize that, but for field application, one important point is that we need to measure the initial water ratio or unit weight accurately. Otherwise, it won't be very, very high accurate. So that's all for my presentation. And these are some colleagues and organizations I want to acknowledge. And that's all. Any questions?
Okay, thank you very much, Professor Yi. And we know that the reuse of Thai can considered as a very potential method in sustainable geotechnical energy. So, do we have any questions? If you have some questions, you can raise your hands up, and we can cancel your mute. So no question. Okay, Professor Yi, thank you very much again. And oh yes, we have one question. Yes, Professor Yesler.
Yes.
Hello, thank you for your nice presentation. I have a quick question regarding the laboratory testing. You indicated that the tests were conducted under dry conditions. Exactly. Would you expect different results if there was some moisture in the specimens? If they were saturated or partially saturated?
Actually, it's good question. And actually, this one paper published in GeoG, Journal of Geotechnical and Geoenvironmental Engineering, ISEG journal. And this only, so far, I only see one paper published on the consolidation of TDA with the saturated TDA. Others, we all work on the dry TDA because in real application, usually the condition is kind of dry. But to answer your question, I would say, based on my experience, it doesn't affect too much because this material has really high permeability. When you compress on the material, the water will come out very quickly. And it may be affect a little bit about the process, but actually it doesn't affect about the final deformation or compression, because it has really, really high permeability. As I mentioned previously in our beta, the application is to use as drainage for landfill. So it means you can think it like this way: the permeability is even higher than sand. It's kind of like rock. So in this process, for example, this process for consolidation, like for distribution of excess forward pressure, actually it's quite fast. It's very short, so it doesn't affect.
Thank you.
Okay, Professor DNS also has a question.
Thank you very much for a good presentation. My question is, what is the latest in utilization of rubber tires? Where is the way forward? What's happening?
Excuse me, what is? I didn't hear you perfectly.
What is the way forward in this subject?
With following?
What is the future of these studies? Where are you going to use them?
If you see the field test, actually, let me show you again. We try to solve the problem for the beta recycle because there are a lot of this material produced every year. So the future application, we try to use this as a lightweight material for example, in civil engineering, for road construction, especially if we have some soft ground. If you use this material, the overbed pressure will be very small because the unit weight, you can see it's quite small. So this is for one application. And we solve the problem for the civil engineering. We try to also solve the problem for the environment. We try to use these materials. So reduce for example, the risk of catching fire, reduce the occupation of the disposal of this material. So that is the future of the material for this technology. For example, I mentioned here, actually, for this pilot project, it's very small. it consumes almost 10% of discarded tiles in a beta produced 1 year. So if we can use it more in future, it can solve a lot of problems.
Okay, thank you.
Thank you.
Okay, thank you. Thank you, Professor Yi.
Thank you, Prof. Gu.
Okay, well, now let's welcome our next speaker, Professor Pu. Professor Pu is a professor in the School of Civil Engineering and I'm sorry. So, Professor Pu is a professor in the School of Civil Engineering, Civil and Hydraulic Engineering at the Huazhong University of Science and Technology. His research interests cover waste disposal and contaminated, coupled flow and contaminated transport in deformable porous media, geoenvironmental remediation, etc. Today, his topic is rapid treatment of hydraulically drained mud slurry using vacuum-assisted fabricated horizontal drain. Let's welcome Professor Pu.
Thank you, Professor Gu, for the nice introduction. And I also want to thank Professor Shi and Professor Tang for giving me this opportunity to present my work here. Can you hear me clearly?
Yes, perfectly.
Okay, great, thank you. My presentation today is on rapid treatment of hydraulically drained mud slurry using vacuum-assisted prefabricated horizontal drain. So in this presentation, I will use the abbreviation PhD to refer to prefabricated horizontal drain. This is my presentation outline. First, I will give some background information on mud slurry, and then I will present several methods that are used for mud slurry treatment. The first one is PhD-based vacuum preloading method. The second one is PhD-based vacuum flocculation combined method. And the third one is PhD-based vacuum solidification combined method. All these three methods are similar. They all use PhDs to facilitate the vacuum preloading. And lastly, I will also introduce a computational model that we developed to predict the behavior of PhD vacuum-induced consolidation. So first, some background. Each year, a huge volume of dredged mud slurries are produced worldwide due to different kinds of dredgings in aquatic environments, for example, in lakes or in rivers, in ports, in reservoirs, and in seas. And it is estimated that about several 100 million tons of such slurries are produced each year. So it's a huge volume. And the dredging can be for different purposes. Some is for instance, the deepening or widening of navigational channels. Some is for environmental remediations. Anyhow, there are lots of dredgings going on, and they produce lots of waste slurry. And these dredged mud slurries exhibit poor engineering properties. For example, it has very high water content. Usually the water content exceeds 200%, and sometimes it's higher than 300, 400, or even 500%. So it's several times the liquid limit. So it's actually in a slurry state. So it's not really a soil, it's more like a mud slurry. It's more like liquid. And because of its high water content, it's usually in a loose state. So it usually has very high compressibility. From the figure here, Professor Morris compiled lots of data for different kinds of dredged materials. We can see that the compression index, CC, usually range between 0.8 to about 2.0, and sometimes it's even higher than that. In contrast, we can see that in conventional soil mechanics, if the compression index CC is higher than 0.4, then we consider it as high compressibility soil. So you can see here the compressibility of mud slurry is usually at least 2 times that. And also because of its high water content, it has very low bearing capacity. Usually the bearing capacity is lower than several kPa, usually lower than 2, and sometimes even negligible, and cannot be measured using conventional testing equipment. And also because of uncontrolled release of polluted water into the aquatic environment, more and more frequently those mud slurries contain contaminants. For example, such as heavy metals, organic compounds, or nutrients such as nitrate or phosphorus and others. So we have this kind of high water content mud slurry. The best way to handle it is to come up with some treatment methods and transform the mud slurry into some kind of materials for beneficial reuse. For example, we can turn it into fill materials for construction, for instance, embankment or levees or dams, etc., etc. We can also make some breaks for pavement, for example, and also people have tried to make it ceramicides. And the key for the treatment here is how we can reduce the water content effectively and efficiently. And there are many methods out there to treat the high water content mud slurry. One commonly used is the prefabricated vertical drain, the PVD based vacuum preload method. This method has been used many years in the field of conventional geotechnical engineering for soft ground improvement. And more recently, people have started to use it for mud slurry dewatering. So the idea is simple. We simply insert the PVDs, the vertical drains, into the ground, and then connect the PVDs with vacuum pumps, and then we apply a vacuum pressure, and then the vacuum pressure can suck out the water and reduce the water content. And overall, the PVD-based vacuum preloading method is economic and effective, but still there are many issues that need to be solved when using PVDs. The first issue is that, as I mentioned earlier, the mud slurry has very high water content. That means it has very low bearing capacity. So in the very beginning, the personnel and equipment cannot access the construction site. They may even sink into the slurry. So usually there is a very long time-consuming pre-treatment before those PVD, those vertical drains can be inserted into the ground. The pre-treatment include some drying or sometimes sulfate deposition or consolidation, depending on the method used and depending on the scale of the site, the construction site. The pre-treatment can be very long, sometimes months or even years. Another issue is that the PVDs can be severely bended because the mud is very soft. After the treatment, after the consolidation, there will be a significant deformation, and because of that, the PVDs will be severely bended, and that can cause a decrease in the transfer of vacuum pressure, and therefore a decrease in the dewatering efficiency. So later on, people began to use the PhD-based vacuum preloading method for mud slurry treatment. Conceptually, it's easy. You just replace the vertical drains, the PVDs, with horizontal drains, the PhDs. First, let me show you the procedures of the PhD-based vacuum preloading method. So first, we need to lay the first layer of PhD at the bottom of the disposal site and connect the PhD with drainage tubes and with vacuum pumps. And then we fill the mud slurry into the disposal site and then start the vacuum preloading to dewater the slurry. And after that, we lay the next layer of PhD, and after that, we continue to place the mud slurry into the disposal site and then start the vacuum pump to pump out water. So we repeat this process over and over again until all the mud slurry is placed into the disposal site. So conceptually, it is easy. We simply replace a vertical drain with horizontal drain, but the benefits are as follows. First, the PhDs are placed before the mud slurry is filled into the disposal site. And because of that, the time-consuming pre-treatment is no longer needed. That alone can save months or even years of time. And secondly, because the PhDs are placed earlier, we can do the filling and also the dewatering of the mud slurry simultaneously. Namely, as we place the mud slurry into the disposal site, we can, at the same time, we can dewater the mud slurry, so we don't need to wait. And because of that, the overall dewatering efficiency is significantly increased. And thirdly, when we use PhDs, the horizontal drains, we will not have significant bending because the drain board will settle together with the soil, with the mud. And therefore, the vacuum transfer efficiency of PhD will be better than that of PVDs. And lastly, during the process of filling of the material, we can also mix in additives into the mud slurry for improved treatment efficiency. For example, we can add in flocculant to improve the dewatering efficiency. We can also add in solidifiers such as cement binder to increase the shear strength. First, we will conduct some small-scale model test to demonstrate that the PhD have better dewatering performance relative to PVD. So we have two model boxes. One has a PVD in the center placed vertically, and then we have another model box in which we have a PhD laid horizontally in the center. This is the test procedure. So we mix the slurry, and then we place the slurry into the model tank, and then we start the vacuum pump. And after the model test, the slurry is turned into soil. So we take out the soil sample for other type of tests, such as strength testing. This figure shows the shapes of the PhD and the PVD as a drain board after the model test, after the dewatering, the whole dewatering procedure. On the left, we can see that the red curve, which is the drain board, we can see that it is severely bended. And on the right-hand side, the PhD was still, the bending was negligible. It's still pretty much flat. And the yellow curve is the soil surface after the treatment. We can see that the soil surface for the PVD was significantly uneven. We have a very uneven surface, which means the treatment will be also uneven. On the right-hand side, the soil surface was much more even relative to the case on the left. We'll also look at the average water content for the model tests with PhD and with PVD respectively. We can see that for the PVD, which is the red curve, the average water content of a slurry decreased from initially 270% to eventually 110%. And for the PhD, which is the blue curve, the decrease of water content is more significant. The final water content is only 60%, which is roughly about 1/2 of that for the PVD. So we can see that the dewatering efficiency of PhD is much higher than that of PVD. Later, we also use this PhD-based vacuum method and combine this with other types of like chemicals, for instance, combine this with flocculant. This is a part of the model test program. We have 6 different groups of tests with different APAM content. The APAM is short for anionic polyacrylamide, which is a common type of flocculant that has been commonly used for water treatment. And in recent years, people have also begun to use this for mud treatment because this APAM is a polymer material. They have very long chains, and these long chains have bridging effects that can bring all the small particles together and to form large flocks. And when you have large flocks, those large flocks can make the soil particles settle much faster. And also you will have a larger pore size, which means the water can flow through the soil more easily. And because of that, when you combine this with vacuum, you have much easier dewatering effect. So this is the height of soil versus time. We tested different contents of flocculant versus no flocculant. So on the top, the natural settling, this curve, the depth curve, that's for the case without flocculant and also without vacuum. So it's all natural settling. This is what happens when you place the mud slurry into a disposal site without any treatment. As you can see in this case, the slurry settled very, very slowly. It took about 400 hours to have a 50% deformation. So the height went from originally 40 centimeter to finally 20 centimeter. That whole process took about 400 hours. In contrast, if you look at the red curve, in this case we added in the vacuum pressure. In this case, the dewatering process is significantly increased. You can see that it took only about 100 hours here to reach 50% deformation. And on top of that, if we further add in the flocculant, we can see that the dewatering process is further increased. In general, the slurry settled faster for increasing APAM content. So overall, we can see that the proposed method gave faster, faster settlement, but also larger magnitude of settlement. In addition to the dewatering efficiency, if we look at the strength, adding the flocculant and the vacuum pressure, that also can increase the shear strength significantly. We look at different flocculant. On the left, we have used APAM. On the right, we used APAM and also lime, some kind of composite flocculant. So on the left, we can see that the shear strength of soil first increased with the APAM content from about 15 kPa to 43 kPa. So that's about 2 times increase because of the bridging effect of the flocculant. And after some point, the strength will decrease with further increase of flocculant because the flocculant is some kind of polymeric material and has high viscosity. And on the right-hand side, we on top of APAM, we further added in lime, because lime has both the effect of flocculant and the effect of binders. So when we're adding both flocculant and lime, the strength can be further increased. So for the highest one, we can have 60 kPa of strength. So in section 4, I will present some PhD-based vacuum and solidification combined method for mud treatment. In this case, so on top of the vacuum preloading, we add in a solidifier to further increase the strength. This is the mud slurry that we use. In this section, we test both clean mud and also contaminated mud. For the clean mud, we primarily look at the dewatering efficiency and the mechanical behavior, such as the shear strength. For the contaminated mud, on top of that, we also look at the stabilization effect of the heavy metals. This is a test procedure. So again, we first mix the slurry and place the slurry in the model tank. Then we start the vacuum preloading, and after that we take out the soil sample and cure the soil samples in a curing chamber, and after that we take them out for other testing. This is the model test program. We have 3 series of tests. In the first case, we use direct solidification. In this case, the mud slurry was solidified at a very high water content without prior dewatering. So as you can imagine, it will have very low strength after the solidification. At the bottom, we also have the PhD vacuum preloading method. In this case, it has no binder, just vacuum preloading, same as in section 2 of my presentation earlier. And in the middle, we have this PhD VPS method, which is a PhD-based vacuum solidification combined method. In this case, we kind of combine the one on top and the one on the bottom. And we test the different initial water content of the slurry. We test the different magnitude of vacuum pressure and different vacuum preloading duration, and also different semen content. But due to time limit, I'm not going to present all of them. So this is average water content versus time for different treatment methods. The black curve on top, that's the direct solidification method. As you can see, the reduction of water content is very small. It went from 300% to 270%. That's because some water is consumed by the semen. And in the middle of the red curve, that's for the vacuum preloading method. In this case, there's no binder, but there is a vacuum that sucked out the water, and because of that, the water content reduced more significantly from initially 300% to roughly 200%. So the dewatering efficiency is higher than, is better than direct solidification method above here. And most interesting is the PhD VPS method. In this case, the average water content reduced even more significantly from 300% to 140%. And more interestingly, you can see that the blue curve drops much more faster than the red curve. That means the dewatering efficiency is improved significantly. And the reason for that is the change in the microstructures. We tested the coefficient of permeability for the soil without a semen binder and with semen binder. You can see that in the early times, when you add in a semen binder, the coefficient of permeability is increased. That's why you have a faster dewatering efficiency in the earlier figure. The increase of permeability is attributed to the fact that the cement hydroreaction at early times has effect of flocculation due to the generation of calcium ions, and also the hydrates have some skeleton building effect. It pulls the particles together and increase the pore size, and because of that, at the very beginning, the dewatering efficiency can be improved for vacuum preloading. And because of that, the mud is solidified at much denser state later on. We'll also look at the unconfined compressive strength. On the left, you can see that the direct solidification method without prior dewatering. We tested different initial water content, and you can see that the strengths, solidified strengths, decreased significantly with increasing water content from 200% to 400%. So this tells us how important it is to lower the water content for further treatment. So on the right-hand side, we have a comparison between direct solidification method with the proposed PhD VPS method. You can see that for initial water content of 300%, the direct solidification method only has a final strength about 10 to like 15 kPa, and on the right-hand side, with the PhD VPS method, the treatment, the strength after treatment can be as high as almost 90 kPa. So the strength can be increased by more than 5 times, sometimes even 10 times or even 20 times, depending on the initial water content. We also look at the MIP test to look at the pore size distribution.
Professor Pu, we have 2 minutes left.
2 minutes?
Yes.
Okay.
2 minutes.
Okay. I will accelerate. So you can see that after the treatment with the proposed PhD VPS method, the pore size was significantly reduced. We have less large pores and have more small pores. That explains why we have significantly increased shear strength. This is the SEM results. I will skip this because of the time limit. We also look at different binder types. We compared the traditional cement binder with the alkaline activated GGBS, which is a granulated plasticine slag. We use different types of alkalines such as lime, MgO, magnesium oxide, and carbide slag. The alkaline activated GGBS have better performance than the traditional cement binder in terms of both strength and the environmental effect. And the previous presenter, Professor Yao Lin, has done a lot of good work on this topic. This figure shows the mass of discharged water, and the blue curve is for the cement as a binder, and the black curves are for the lime activated GGBS. And you can see that more water was sucked out. The mass of discharged water can be increased by 50% when we replace the cement binder with GGBS binders. And because of that, the strength was also increased significantly. On the figure, you can see that the proposed PhD VPS method gave much higher strength than the direct cement solidification. The increase is about 10 to 60 times. And as for the binder, the lime GGBS binder gave also much higher strength than the cement binder. The increase is about 4 to 11 times. So in addition to the clean mud, we also look at the contaminated mud to look at the to look at the stabilization effect. I will go quickly here. So here, this is the leaching concentration of heavy metal zinc, and you can see that for the direct solidification, that has the highest leaching concentration. And then when we use the PhD VPS method, that can reduce the zinc concentration by about 50%. so a significant increase in the stabilization effect. The reason is that it caused the change in the speciation of heavy metal. When we treat the mass slurry with PHD-VPS method, especially when we use the MgO and GGBS as a binder, there are less unstable fraction of heavy metal and more stable fraction of the heavy metal. And lastly, I will present some computational model that we developed for PhD-induced consolidation. Because when we use this PhD-based vacuum method in the field, we need to decide how we design this PVD, how long we need that, and what is the lateral spacing and a vertical spacing of the PhDs, especially when we have complex conditions such as layer soil profile and etc. etc. We need to design this whole thing. We need to have a tool to analyze the change of water content, the change of the sediment, and etc. etc. So we need to have a numerical model to analyze the deformation process. We developed a model, and then we validated this model by comparing with other analytical solution, and also with numerical model, and also compared with a large-scale field test conducted by Shisha back in 2014, and again the numerical model performed well with the field testing data. My presentation was pretty fast, so here's a list of my publications on this topic. If you're interested, you're welcome to download and read. So that's all for my presentation. Thank you very much.
Okay, thank you very much, Professor Pu. It's a very nice presentation, but unfortunately we don't have time for questions, so I'm sorry, we have to move on. So next speaker is Professor Ningjun Jiang from Southeast University. Professor Jiang's research areas include biomediate geotechnics and soil remediation. He received a Ferdinand Award from Canadian Geotechnical Society in 2019. Dr. Jiang is editorial board member of Soils and Foundations and Environmental Geotechnics. Today, his topic is engineering performance of biostimulated MICP treated on calcareous sand. But Professor Jiang asked because he is now isolated in a hotel where there's a very poor access to the internet. So he sent me his pre-record presentation, and I will show the presentation on behalf of Professor Jiang. So I'm sharing my, yes. Okay.
Good afternoon, everyone. I'm Ningjun Jiang from Southeastern University in China. Firstly, I would like to thank ISEG Organization Committee for their invitation to deliver a presentation today. So today, the topic I would like to talk about is engineering performance of biocemented calcareous sand treated through biostimulation. So as you may know, calcareous sand is a very special earth material. It comes from the carbonate skeleton of marine organisms and is widely distributed in tropical regions around the world. So calcareous sand particles are normally highly angular and their surfaces are quite rough. So calcareous sand itself is typically high in water ratio, crushability, and compressibility, and its strength is relatively low. So due to these reasons, so when used as foundation material, calcareous sand has to be, reinforced to meet the design construction requirements. So then microbial-induced calcite precipitation, or MICP, is a promising soil improvement technique and has gained a lot of attention in the recent years. So the idea of MICP is that nature urealytic bacteria could produce urease enzyme. So this enzyme then could hydrolyze the urea to produce carbonate and ammonia. And at the same time, the environment pH is also elevated. So then with the slightly alkaline condition, then if there are calcium ions present, then the calcium ions can react with carbonate to generate calcium carbonate precipitation or calcite precipitation. This precipitation, when present between lucent particles, can serve as interparticle bonding and increase the overall mechanical strength of the sand. So currently, the research in MICP is quite active worldwide at all scales, ranging from micro scales to macro scales to the field scales. And here on the right-hand figure, I listed a few featured researches at different scales. And due to time limit, I will not talk about them in details. Okay, so then the approach to achieve MICP, right? There's two. One is biostimulation and the other is bioaugmentation. So bioaugmentation is a more typical way, meaning that a standard or a known bacteria species is cultivated in the lab, and then the bacterial solution is injected into the ground to trigger MICP reactions. So, but the disadvantage of the bioaugmentation method is that the compatibility of the injected bacterial solution with the nature environment is questionable, and sometimes the injected standard bacteria may not survive so long time. Then in addition to bioaugmentation, then biostimulation is an alternative way to achieve MICP. And there's also two approaches to achieve biostimulation. One is ex situ, the other is in situ. Ex situ means that the urealytic bacteria is extracted, isolated, and purified from the sampled nature soil. Then the bacteria are enriched in the lab and then re-injected into the ground. So through this method, of course, the compatibility of the injected native bacteria and the nature environment will be much better compared with that in the case of bioaugmentation. However, the processes involved in ex situ biostimulation are quite complicated, right? So then it comes to the next approach, the in situ biostimulation. In this method, instead of injecting bacteria, only carefully designed enrichment medium will be injected, and the medium can stimulate the growth of native urealytic bacteria in the soil, in the nature soil, and then it can trigger MICP. So compared with the rest two approaches, it's much simpler, and it's much simpler, and also the whole process is relatively easy, and there's no problem regarding the compatibility of bacteria and the nature environment. So in this study, we will focus on the in situ biostimulation method. Okay, so actually this is a very big project. So the biostimulated MICP for calcareous sand stabilization. In this big project, we look at three aspects: optimization, performance, and application. For the optimization, then we focus on the phylogenetic characteristics, erase kinetics, and chemical reactions by doing solution batch test, column culture test, and genetic sequencing. For the performance aspect, we've characterized the biocementation level, shell strength, and compressibility by doing direct shell test, traxel shell test, and odometer test. And finally, for the application aspect, we focus on ground improvement, coastal erosion control, heavy metal immobilization by doing 2D tank test and hydraulic film test. So in today's presentation, I will mainly focus on the first two aspects, optimization and performance. Okay, so firstly, let's look at the optimization, right? So here, firstly, we performed the solution batch test. So the purpose of solution batch test is to find out what are the most significant factors that control the enrichment of indigenous urolitic bacteria, or stage 1, right? So actually, as mentioned, right, the biostimulation has two stages. Stage 1 is to stimulate the growth of bacteria, and stage 2 is to form biofermentation, right? So here, we only look at stage 1, what are the most significant contributing factors. So for the test, right, we mixed 1 gram of beach sand with the enrichment solution. Here we have 3 types of enrichment solution. YE is extract, ME multi-extract, and NB nutrient brush based, urolitic enrichment solution. Because in this solution we also have urea inside. Okay, so when they are mixed, then they are subject to shake incubation for different periods, and then the samples are subject to pH, electrical activity, and ammonia concentration measurements. Also, we performed the viable cell number counting. Okay, through this test, then we performed the analysis of variance to get the p-values. And a very small p-value means that a certain variable is very significant, right? So from this analysis, we can clearly see that the incubation time, right, or the stimulation or enrichment time, then the concentration of urea in the enrichment solution, as well as the medium type, are the most significant factors that may affect the enrichment stage, right? So then, in order to further determine what are the optimized, like urea concentration and stimulation time, then we did the soil column test. So it's quite similar to the solution batch test. Only different is that we directly inject the enrichment solution into the soil column, and after a certain period, then we take soil samples and measure the urea concentration and ammonia concentration. So here are the results. So clearly, if we see the black lines and dots, we can see that with the increase in urea concentration, right, from 50 mole to 100 to 170 mole, then the ability of the enriched bacteria to consume urea concentration also becomes higher, right? It means that the generated urolitic activity is higher, right? So from this test, we can see that actually 170 mole or 100 gram per liter urea is sufficient to effectively induce, biostimulation, right? So that's already a lot, enough urolic bacteria enriched at this concentration. Then also we find that after 48 hours, regardless of the medium, whether it is YE or NB, we can see, right, after 48 hours, all given urea has been consumed, right? It means that after 40 hours, it's already done, right? We already have sufficient amount of urolic activity from the stimulated bacteria, right? So that's why we choose 170 more urea and 48 hours our following tests. Okay, so then it comes to the performance aspect, right? So in this part, okay, so firstly, I would like to introduce the material and testing method. So the soil sample, again, is sourced from, Waikiki Beach in Hawaii, because this is a study I performed in Hawaii. And then we perform the enrichment medium, which contain either extract or nutrient brush and urea, right? So this is a composite material. And then we have cementation solution, which aims to generate biocementation, right? Within the cementation solution, there are calcium, urea, and trace nutrition additive. Okay, so then for the first 48 hours, right, the enrichment medium was percolated on the surface, through the surface of the soil sample to stimulate the growth of the native bacteria, as mentioned, right? 48 hours is the optimized time we found. And the concentration of urea within enriched medium is 170. Okay, then after 48 hours, then we, percolated the cementation solution once a day for 5 to 10 days. So the aim of this percolation is to generate biocementation at different levels, right? The longer period of percolation we perform, then the higher cementation level we expect. Okay, so then after that, right, we got the biocemented sand samples. Then we performed the cementation content measurement and direct shell test, track shell test, and ultimate test. So here is the overview of the experimental program, as you can see, right? So we have 2 enrichment medium. Then the soil samples are prepared at 2 different relative densities. One is low, 16.2%. The other is high relative density, 54.6. Then for biocementation treatment, right, we selected 2, cementation solution concentration. One is 0.3 mole, the other is 0.5 mole, and 2 percolation periods, 5 days and 10 days. So this will give us different cementation levels. Okay, so firstly, let's see the cementation content results. So here there's several columns, right, divided into 4, boxes. Within each box, right, from the left to right, we can see that the cementation content increases. Actually, from the left to the right, we can see that either the cementation solution concentration increases or the, treatment period increases, right? So here, then we can conclude that higher cementation solution concentration as well as longer treatment period could lead to higher cementation content. And this is true for all 4 cases with different enrichment media and relative density. And meanwhile, we find that if we compare these 4 boxes, actually the initial relative density and the medium type do not significantly influence the cementation content level. Then we also actually performed the microscopic observation using optical microscopes. So in picture A, so this is uncemented sand, as we can see, the loose sand without any cementation or bonding between particles. Then for figure B, then this is a low cementation level case. We can see a little bit, interparticle bondings, but not that obvious. However, for the heavily cemented case, which we have 6.33% cementation, then we can see quite obvious, wide interparticle bonding or cementation between the sand particles. In addition, we also see, many calcareous sand particles are coated by this kind of white cementation, right? So these 2 graphs can prove that the biocementation are effectively generated. Okay, so next, let's see the direct shell test results. Firstly, is the stress ratio displacement relationship. Obviously, so here I just pick up 1 representative case, right? So with the increase in the normal stress, then the peak shell stress ratio, the peak stress ratio drops, right? And also the strength corresponding to the peak also increases. And if we look at the vertical displacement, horizontal displacement relationship, so at low normal stress, 50 kPa, then the soil is quite dilated. However, if the normal stress is like 600 kPa, right, like when it is elevated, then the dilation of the soil is kind of suppressed, right? It becomes more contractive. Okay, so that's a general, shell behavior during direction test for the biocemented case. Then we systematically summarize the peak stress ratio results and correlate it with the cementation content. So the left-hand graph is low initial density case, and the right-hand graph is high relative density case. So here we can see that firstly, the peak stress ratio increases with cementation case. So this is true for all samples, right? So it means that cementation can help improve the shear strength, right? Peak shear strength, peak shear stress of, the calcareous sand, right? However, this increase, right, is diminished with higher confinement, right? So like for 50, we can see the slope is quite large, right? So this increase is quite significant. However, at 600 kPa normal stress, then with increasing concentration as cementation content, then the improve in peak stress ratio is not that significant, right? So this diminishing effect is obvious. And finally, it seems the initial density does not have a quite obvious effect, impact on the peak stress ratio. Then, based on the direct shear test, we also obtain the cohesion and friction angle based on the Moore-Coulomb theory. And here, this graph shows the cohesion versus cementation content. So obviously, with the increase in cementation content, cohesion is increased, right, due to the formed interparticle bonding, right? So cohesion, improvement in cohesion is quite obvious. And if it is compared with previous studies, we can see that at the same cementation content, right, the cohesion in our study, measured in our study, is higher in two previously reported studies, meaning that potentially this biostimulation method is more effective because these two previous studies were all about bioaugmentation, not biostimulation. And secondly, here I didn't put the friction angle data, but actually we find that the cementation content does not significantly influence friction angle, no significant improvement or reduction, right? So only cohesion is apparently affected. Okay, so next is the CU structural shell test, right? So on the left-hand graph, that's the picture taken at the end of two CU structural shell tests. One is on the 400 kPa confined pressure, the other is on the 50 kPa, right? On the 400 kPa, right, the high level of confining pressure, we can see clear shell band, right? However, for 50 kPa, it's like barging. Then on the right-hand side graph, so this is the effective stress pass graph. Okay, so on this graph, the dotted lines represent the uncemented, right, the clean sand, and the solid lines represent biocemented sand. So here we didn't vary other parameters like cementation, solution concentration, treating time, sort of things. We only pick up one fixed cementation level. Okay, so from the effective stress pass graph, firstly, we can see that for both uncemented and biocemented sands, they exhibit strength hardening behavior, right, because they CU test. And secondly, after biocementation, the sand exhibits the shear behavior like dense sand, right? So compared with the uncemented case, right, the effective stress pass shifts to the right, right? And this is especially true at lower effective mean stress, right? So for clean sand, it's more like loose sand, right? Like loose sand. However, after biocementation, it becomes more like dense sand. Okay, then finally, if we look at the critical state line part, right? In some samples, maybe the critical state is not fully reached, but in general, we can see that after biocementation treatment, then the slope of the critical state line increases. So, and it is higher location of the critical state lines. The biocemented samples are higher than that of untreated samples. Then from the CU structural shell test, we also use Moore-Coulomb theory to get the peak and the residue cohesion and friction angle. right? So left-hand side graph shows the peak state, and the right-hand side picture and shows the residue state. So from this one, we can see that. So the red one represents the high cementation level case. The solid black one represents the low cementation level case, and the dotted one shows uncemented case. So obviously, with biocementation treatment, right, the cohesion, the effective peak cohesion increases from 0 for uncemented case to 41.6 for the high cementation level case. And however, if we look at the effective friction angle, right, actually it does not change too much. So it means that the peak friction angle is sort of independent of cementation content. Then for the residue state, so firstly, we find that the cohesion is fully mobilized, right? So there's no cohesion at this state. So it means that all effective bonding has been broken as a residual state. And secondly, if we look at the effective residual friction angle, right? Again, it does not change too much with the cementation content. Okay, so finally, it's the ultimate test or one-dimensional compression test. So from this test, we can obtain the compression curve. So here, because the soil samples have slightly different initial water ratio, so here we perform the normalization. So the vertical axis will be the normalized water ratio, and the horizontal axis, the vertical stress. So we perform it, and from the black one to the purple one, then the cementation level increases, right? So from the graph, you can see that with the increase in the cementation content, then the compression curve generally move upward, right? So the transition becomes more steep, right? More abrupt with the increase in cementation content. And accordingly, if we look at CC, the compression index, and CS, the swelling index for this part, right? So with the increase in cementation content, CC increases and the CS reduces, right? And finally, if we look at the rebound state, interestingly, right, even if the cementation content different, but the slope for this part, or we can say CR, the rebounding index, is very similar among these cases. It means that the rebound state actually is kind of independent of cementation content. And this can further prove that at this stage, the soil has been fully, the interparticle cementation has been fully broken. And during the ultimate test, we also evaluated the relative breakage, right? So firstly, I would like to briefly introduce the concept of relative breakage, right? As you can see on the left-hand graph, so this is the typical particle size distribution curve. So in this graph, the black one represents original PS, the particle size distribution curve of clean sand. And the blue one represents the particle size distribution curve of biocemented sand after loading. I mean, at the end of the compression test. So interestingly, we can say that at the final particle part, right, for the parts, smaller than 0.6, the particle size distribution curve moves to the top of that of clean sand. So it means that actually we have more fine particles generated during the compression process. So then the relative breakage is defined as a ratio of the area of OFGO and the area of ABOG. As you can imagine, right, if we have more fine particles, right, generated during compression, then this ratio, the area of OFG will become larger. So the relative breakage will become larger as well. Okay, so then we plot the relative breakage BR with cementation content, right? The data from different cases. Okay, so firstly, actually, we also did a control test. So for the clean sand, so after compression on the clean sand, actually, we didn't see any noticeable change in particle size during curve. It means that the calcareous sand particle itself does not break, right? So we can see that the generated fine particles during the compression of biocemented sand are from the broken interparticle bonding. However, with increasing cementation content, the BR value reduces significantly. It means that if we have a lot of cementation content, then it is unlikely that, or in other words, the breakage of cementation bonding will be less severe, right? Less severe. And also, we find that with the increase in the initial relative density of the soil sample, then the BR values are also lower. That's because, for initially low relative density samples, then the interparticle bonding or cementation are more likely to locate it in, better places to form better bonding, right? So the relative breakage will be smaller. Okay, so these are the mechanical performances we obtained from series test, and here are the main conclusions. Firstly, so we find that 170 more urea and 48 hours stimulation time are sufficient to stimulate enough indigenous ureatic bacteria. And secondly, we find the high biocementation level can be achieved by applying higher cementation solution concentration and for longer treatment period. And thirdly, in the direct shell test, shell stress ratio, so here I mean peak shell stress ratio increases with cementation level, but is suppressed with elevated confinement. Then in the CU traxel shell test, effective cohesion increased substantially with cementation content. Friction angle, however, is independent of it. Then in the automated test, the compressibility of calcareous sand and the bonding breakage during compression are dramatically reduced after subject to biocementation treatment. So through these observations, we can finally conclude that biostimulated MICP could effectively stabilize calcareous sand without introducing, bacterial cultivated in the lab. Thank you for listening. And if you have any questions, please feel free to send email to jiangn@seu.edu.cn. Thank you.
Okay. Again, we are very sorry about the trouble. And since Professor Zhang is not here, we will not have questions for him. And the next speaker is Professor Xiaojing Ran. Professor Ran is assistant professor in the College of Civil Engineering and Architecture, Zhejiang University. His research focuses on life cycle assessment and costing of cement and concrete production, carbonation of MgO and cement and their applications in civil engineering, reviews and recycle of industrial and construction waste as construction materials, straining, hardening, and self-healing behaviors of cementitious composites, 3D printing concrete technology. Today, his topic is life cycle assessment of alternative materials used for stabilization and solidification in some cases study. Now, let's welcome Professor Ran. Professor Ran, you can stand now. Professor Ran, we cannot hear you.
Okay, can you hear me?
Yeah. Yes,
okay,
yes.
sorry.
Okay.
I muted myself. Okay, so good afternoon, everyone. So I'm very happy to join this web seminar. And today, my topic is life cycle assessment of different alternative materials used for stabilization and certification. And now I'm working in Zhejiang University. So my presentation can be divided into 4 parts. The first part is about introduction, then is the methods that we use. The third part is about the results and discussion, and finally is the conclusion. So first about the introduction, as we all know, the SS or stabilization and certification is a process that results in the immobility of contaminants in hazardous wastes through reactions with additives or processes. And we all know Portland cement, it is very cost effective and it is widely used in SS. But its production process is quite energy intensive and emits a high amount of carbon dioxide. Nowadays we try to achieve the goal of carbon neutrality. So if we use too much Portland cement in SS, it is not quite environmental friendly. So we should search for other materials that is low carbon. And I will show you 2 figures first. First is about the materials flow of ordinary Portland cement manufacturing. And we all know, first you need to get some raw materials to produce cement. And I know it is quite boring, but I want to introduce this first. And you need lime, alumina, silica, and iron oxide. Then you need crushing, grinding, and blending to make this is blended mixture. Then the very important procedure, that is the calcination, and you can get some clinkers. Then finally you add some gypsums to Portland cement to produce the commercial products. And we all know the carbon dioxide emission that it can be divided into 2 parts. The first part is about the direct carbon dioxide emission. The second part is the indirect carbon dioxide emission. And the direct carbon dioxide emission comes from the calcination of carbonates, the calcium carbonates. And the indirect carbon dioxide emission comes from the use of fuels. If you use some coal, if we use some natural gas, it will produce some carbon dioxide. And in terms of OPC, around 0.8 ton carbon dioxide will be emitted to produce 1 ton OPC. But actually, it depends. It really depends. And it depends on the locations, depends on the regions, or depends on the technologies you used. So this value, 0.8, may not be that accurate, and it is highly variable. So in terms of this, we need to search for a low carbon binder for the use of SS. And the second figure is about the process flow, indicating the energy, heat, or gas or solid emissions for the generation, for the production of OPC. And it shows some energy you need input in, and also it will emit some gases or solid wastes during the production of OPC. Here comes the question. So are these binders, that so-called low carbon binders or industrial waste, are they really low carbon? So here we need to use the very powerful technique or the method that we call the life cycle assessment. And the life cycle assessment, it can be divided into 4 parts. And the first is about the selection of the boundaries of scope and system during an LCA. The second part is searching for first-hand or second-hand inventories of a product or a process. That is the evaluation of the obtained data using an impact assessment method. Finally is the interpretation of outcomes and providing recommendations for improvement. So there are numerous methods that we can use to evaluate the environmental impacts of some materials or the procedures. And the most The widely used one is the Earthquakeinduced 99 or IPCC 2013. And Earthquakeinduced 99, it can be divided into several parts, and you can get a number of midpoint categories such as the climate change, the radiation, the land use, and these environmental categories can be further categorized into 3 groups, and that is the damage to human health, damage to ecosystem, or damage to resources. And after you get the endpoint results, you can weigh these values, and finally you get the interpretation. And in terms of IPCC 2013, it is usually used to obtain the carbon dioxide emission during the production of certain materials or a certain process. So still, of course, we need to first talk about the ordinary Portland cement. And this figure is about the normalized impact categories with respect to climate change set at 100%. And as we can see from this figure, the fossil fuels are identified as the largest impact category to produce the OPC in the USA and Europe. But due to the confidential issues, China's actual carbon footprint due to the cement production is still not fully unknown. So in terms of this, we have several measures that to increase the sustainability of OPC or Portland cement. The first is about the energy type and efficiency. We need to increase this. And for example, we use a lower carbon fuel like natural gas. And the second is we need to increase the efficient grinding and conversion from a wet to a dry process. And the third method that we can use the replacement of the out-of-date piling lines or introduction of a high volume of supplementary cementitious materials. Okay, so previous speakers also mentioned some binders like alkaline activated cement, and actually this type of cement is quite popular in my research area. And nowadays, numerous researchers, they investigated the performance of alkaline activated cement, whether they are used in the concrete or used in the SDS. So actually, I want to give a very brief definition of ASC. That is, alkaline activated cement is considered to be a more sustainable material than OPC, which is produced by a reaction between the aluminum silicate-rich materials and alkaline activators. And in terms of its advantages, ASC shows greater sustainability than OPC, and ASC demands lower energy and carbon footprints. However, there are some uncertainties. In some cases, ASC may show a higher global warming potential compared with blended cements, which could be related to the production of alkali that consumes a large amount of energy. And as we know from the definition, to produce or to prepare the alkaline activated cement, you need a large volume of the alkaline. And this alkaline, in terms of this alkaline, its production process may be energy intensive. So to further add some environmental burdens to the whole process. And the second part is about the magnesium bearing cement. So first, I will briefly introduce about the MgO, because MgO is the major component that is used in the magnesium bearing cement. And the magnesium oxide produced from the dry root, the dry root is about the calcination of the magnesite. As you can see from this equation, it will produce the magnesium oxide and the carbon dioxide. And the second part is about the wet root. The wet root is about to obtain the MgO from the seawater, brine, or rejected brine. You need some alkaline bases to produce the magnesium hydroxide first. Then you calcinate these products to produce the MgO. But from our experiment, that we find that the MgO produced from the dry root has an advantage over the MgO produced from the wet root in terms of the overall sustainability. And you can see from this figure, the left one, MgO from the dry root, it has a lower single score compared with the MgO from the wet root. And however, in terms of the dry route. Magnesite, the major production countries is China compared with in terms of the MgO production. So if you want to use the MgO from other countries than China, the transportation, is needed, and it will also lead to some environmental impacts concerning the transportation of MgO. Then, there are several types of the magnesium-bearing cement. And for example, the carbonated MgO cement, magnesium silicate hydrate cement, magnesium phosphate cement, magnesium oxychloride cement, and magnesium oxysulfate cement. And the magnesium phosphate cement, magnesium oxychloride cement, and the magnesium oxysulfate cement, they all show very, reveals rapid setting and hardening properties, and which is quite useful in the process of SS. So they are commonly used in a lot of applications. And first about the carbonated MgO cement, and we published a lot of papers regarding this area. And as we know, the MgO cement will acquire the compressive strength via sequestration the carbon dioxide. So it will then lead to the reduction in the pore volume and the improvement of the microstructural process. And the MgO, the carbon dioxide, can be permanently captured in the form of stable hydrated magnesium carbonate. However, the carbon dioxide sequestration potential of MgO used in the SS in a natural environment is still unknown, because due to the lack of the geochemical model. And you can see from this figure, the MgO will first react with water to produce some layers of brucite on the surface of the particles. Then it will also further react with carbon dioxide to further produce the HMCs. That is called the hydrated magnesium carbonates. And then it will lead to the production of the pores and lead to the strength improvement. And previous speakers also mentioned about the MICP. I know, yeah, MICP is also a quite popular research direction in this area. And it uses the bacterial, and it uses some calcium-bearing salts, like calcium chloride, calcium, salts. And actually, previously, we also conducted some research regarding the use of MgO in MICP. And we also introduced the reactive magnesium cement and the bacterial, and it will produce the hydrated magnesium carbonates to solidify these sands. And the results are quite good, and I think it is a very promising field. Then is the magnesium silicate hydrate cement. Actually, magnesium silicate hydrate cement can be synthesized by the reaction between MgO and a silica-rich source, such as the microsilica and the rice husk ash in the presence of water. And this salt, the sodium hexacetal phosphate, instead of PCE, and is used as a reducer, water reducer. However, this one, when you use this water reducer, it may add additional environmental loads to the MASH binders. And also in terms of the solid waste, normally people researchers use the microsilica. And however, some researchers also use the rice husk ash as the solid waste to produce the MASH cement. And however, this silicon dioxide should be amorphous, and then if it is crystalline, and the MASH, the strength of the MASH is quite low, so it may not be very effective in the SS. Then is the magnesium oxychloride cement. And MLC, we call this MLC. MLC is a type of the non-hydraulic cement by the reaction between the MgO and magnesium chloride. And several very important phases like phase 3 and phase 5 are the major products that formed at an ambient temperature, which contribute to the fast hardening of cement paste. And there's a study that is over the past 15 years, the rate of carbon dioxide will be further recaptured into the MLC. And it is found that the rate of carbon dioxide capture is about 0.07 kilograms per square meter sample per year, and accounting for 20% to 40% CO2 resequestration owing to the natural carbonation of a 15-year time frame. So this equation is about the carbonation of MOC. So when you perform an environmental assessment of MOC, its capture potential of carbon dioxide should be also taken into account, and to make it a more comprehensive evaluation. That is the magnesium phosphate cement. Actually, this one, we conducted several research about its feasibility in the 3D printing, and found it's quite effective because it is rapid setting. And MPC is also a type of ceramic via the reaction of monopotassium phosphate and MgO, and the produced crystal structure is this one, and struvalite, and contributing to the rapid strength development in binders. And produce 1 ton of MPC and OPC, the energy requirement is quite different, and the energy requirement of MPC is much lower compared with that of OPC, and the carbon dioxide emission of MPC is also only about 0.32 ton to produce 1 ton MPC, so which is almost 3 times less compared with the counterparts of OPC. That is the magnesium oxysulfate cement, and magnesium sulfate cement it consists of MgO and the magnesium sulfate, and I performed several evaluations regarding the overall sustainability of MOSC and OPC, and we found that is the ratio of MgO to magnesium sulfate is irrelevant to the final environmental impacts, and they're quite similar. And the overall sustainability of MOSC is comparable with that of OPC, so which means it is not quite sustainable. And in terms of the carbon dioxide emission, and an interesting thing is that the production of MOSC emits a much higher carbon dioxide emission compared with OPC, which means if you want to achieve the goal of carbon neutrality, you should not use the MOSC. Instead of, you should use OPC. Maybe it's cheap and it is widely used. So MOSC may be not very favored in terms of the carbon dioxide emission. That is the calcium sulfur aluminate cement, and maybe I mentioned in the previous slide that is in terms of OPC production, you need to calcinate the limestone, that is the calcium carbonate, to emit a lot of the carbon dioxide. But in terms of CSA, a source of sulfur is needed in the manufacturing process, and an additional extra source of aluminum oxide is required due to the limited source of bauxite, which adds to the environmental burden due to their mining and refining. So the sustainability of CSA is highly dependent on the local or regional availability of bauxite. But in terms of its advantage, yeah, of course, it has a lot of advantages. For example, its production emits less carbon dioxide emission than OPC, because you don't need to calcinate the limestone, that is calcium carbonate. So the direct carbon dioxide emission is much lower, which led to the lower overall carbon dioxide emission. Meanwhile, the manufacturing process efficiency of CSA is much higher compared with OPC. And via the use of industrial waste, the CO2 cement is more effective in the process of SA sustainably. Then here comes the question, that is it sustainable to use industrial waste in SS? So yeah, I have some comments, critical comments. That is, first, actually some industrial waste may be quite radioactive. Actually flash is widely used, but in some cases, some flash also may be very radioactive. And the red mud, nowadays I know there are a lot of publications regarding use the red mud in the SS, but according our preliminary results. The red mud is quite radioactive. It cannot be used solely. It may, combine with other binders, but in practice, it is very difficult to judge whether this type of red mud is radioactive or not. So I think currently it is of great importance to judge this red mud in advance in practice. Another thing is allocation, the allocation of the environmental burdens. As we know, if we want to produce the PFA, the fly ash, it is the byproduct of the electricity. And in terms of GGBS or slag, it is the byproduct of the pig iron. But actually, it is not very fair to consider the PFA or GGBS as a pure industrial waste, because if you produce a lot of electricity, it will give you a lot of environmental burdens. But some claim that you need to allocate the partial environmental impacts to the production of PFA or GGBS. So there are several allocation methods. That is allocation by mass, allocation by economical values. So after you adopt these allocation procedures, industrial waste may not be quite sustainable. But actually, people prefer the allocation, no allocation. Actually, but in our study, no allocation is also a kind of allocation process. So if you just adopt no allocation, so they are just consider them as industrial waste, I think they are quite sustainable. But if you allocate these environmental burdens by mass or economical values to the PFA or GGBS, so the industrial waste may not be that sustainable. So here comes the equation that used to allocate the environmental burdens through mass or economical values. Another thing is, nowadays in some developed countries like UK, they already announced that a shutdown of all coal-fired power stations will be achieved in the near future. And GGBS, also another very commonly used material.
Ran, you have 2 minutes left.
Okay, almost finished. I also face a similar situation in these developed countries due to the upgrade of the technology in the steel industries. So which also leads to a great decline in GBS. So nowadays, China and India, they are the major countries that produces the flash and GBS. So if you want to use these materials in other countries, the carbon dioxide emission associated with the transportation should also be taken into account. So finally is the conclusion. So I think first it is of paramount importance that the carbon dioxide recapture potential of the materials should be included in a life cycle, so which may alleviate the global warming potential induced by their production. Secondly, some alternative materials, including AIC or CSA, may outperform OPC from the perspective of carbon footprint and overall environmental impacts, while some are not really low carbon. Thirdly, the introduction of local solid waste in the alternative materials could further reduce the overall environmental burden to some degree, but some solid wastes should be re-examined. Okay, finish. Thanks.
Okay, thank you very much, Professor Ruan. And do we have any questions? Please raise your hands and we will unmute you. Do we have any questions? Okay, well, thank you very much, Professor Ruan. And we all know that the sustainable materials for the SS and it are very important and have very great potential in the application. So thank you very much. And if we have any questions, we can communicate with Professor Ruan privately. That's all for the session this afternoon. We thank all the 6 speakers for the interesting and very useful presentations for us. And then now I would like to close the session and welcome Professor Chaoshen Tang for the closing ceremony. Professor Tang, you please turn on your voice.
Okay, can you hear me?
Yes, yes.
Okay, ladies and gentlemen, good afternoon, good evening, and good morning. I should say this has been a wonderful 2 days. We have 24 speakers from North and South America, Asia, Oceania, Europe, and Africa. The topics covers a wide range of aspects in environmental geotechnology. I think all of us enjoyed the talks, and many of us got inspired by these exciting works in addressing the new challenges and opportunities in reaching carbon neutral targets, advancing sustainable infrastructure, solving pollution problem, controlling the pandemic, and so on. Also online, it is a good time to make friends and build up connections. I would like to take this chance to thank all the speakers for your time. Your wonderful talks make this event a big success. I would also like to thank the guests and the participants. Thanks for your support to ISEG event. I would like to thank all the organizing committee members for your hard work to prepare for this event during the past 1.5 months. Due to the limitation of preparing time, this may not be a perfect event, but this is a good start for the communication among researchers, policymakers, practitioners act in the areas of environmental geotechnology. The challenges and the opportunities are still there, and our mission is not completed yet. Therefore, we will continue to hold ISEG webinar series or conference, and we're looking forward to your continued support. Thank you, and see you at our next event. So thank you all. Now, I think we come to the end of this webinar, and thank you all for the contribution.
Okay,
Bye-bye.
see you. Bye-bye.
See you next time.
Good. Thank you for all our people. Okay, thank you.
Thank you.
Thank you, everyone. Bye-bye.
Yeah, thank you very much.